Good day. My name's Christopher Patton. I'm the CEO and co-founder of Alphacore Limited. Alphacore is an advanced technology development group. We're a New Zealand-based company, but we operate outside of the United States. We've been advising members of the United Nations and the African Union and Australia for over 20 years now. Our core specialty is zero-emission, zero-pollution technologies. We've also developed five-star eco-resorts. We've worked recently with the United Nations on the Innovation Pavilion at the Climate Change Pavilion for COP. We've been invited to do that now for 3 years in a row. So we're one of the 3 people you'll be speaking to at the Innovation Pavilion if you're looking to reverse the decline of your country and save your species from extinction. Over the last 20 years, what Alphacore has become successful at is taking any form of heat and converting it into useful power or work. How we've done that is we've developed motors, turbines, pumps, and compressors that can run on bioethanol derived from kelp or agricultural food waste. We've also worked with hydrogen. We've worked with heat cogeneration, so we can use external heat instead of internal combustion, which is very important if you want to increase the efficiency of how you convert heat into power. In the last 3 years, we've focused primarily on ocean and island preservation. We've been working on projects in the South Pacific now for almost 2 decades. We've seen firsthand what climate change can do to an island and the ravages on coral reefs from all the acidity. So we decided that the best use of our resources were to put together programs that could reverse the decline of islands and safeguard the ocean. Some of the areas of applications that we've concentrated on are power on demand, and that's without the use of fossil fuels, coal, or nuclear energy. Air to water systems, and that's taking moisture out of the environment and converting that into drinkable clean water with very small amounts of power. We have clean heat sources, and for us, that's cooking fuel primarily. One of the biggest issues that we run into in some of the projects is that we're in territories where they're still cooking with wood or car tires or plastic over an open flame, and it causes a tremendous amount of health issues: glaucoma, blindness, heart disease. So we've concentrated on working with food-based bioethanol, and that's from agricultural waste, by the way, and also kelp-based alcohol, which can be used as a cooking fuel and also used to run engines and boats. We also have waste remediation division, where we concentrate on septic waste remediation, and that's with plasma, not with septic fields. So we've eliminated viruses and any toxicity or septicemia that may take place in the event that there's a hurricane or a storm. But we also work on plastic waste annihilation, because we believe that we've lost the war when it comes to upcycling plastic. There's too much of it now. We're going backwards. So we are developing programs that will carbonize and destroy the plastic at the point of use. 3 years ago, we were asked by members of the UN to look into a very large-scale waste remediation project. Ocean dead zones. We have a lot of experience with regenerative agriculture for feeding a lot of people. And we know that when you use petroleum products for fertilizer or pesticides, when you water your fields or it rains, these products go into the river and they cause the oxygen levels to go down, as well as all the animal waste that's coming in with it. When these move down into a coastline, they reduce down the oxygen levels, they bring up all the nitrogen levels and the acidity of the ocean, and you get algae blooms, and then it just wipes out all the life in the area. Unfortunately, what we've learned recently is it's not just the coastlines that are being affected by these algae blooms and the reduction of oxygen. It's moving beyond the coastlines now, and it's spreading into the ocean. So let's look at this from a regenerative agricultural standpoint. Nature doesn't have waste. Nature just has surplus of unutilized natural resources. So if we were to look at this nitrogen that's coming down the river with all the animal waste, maybe we can come up with a way of grabbing that and converting that into a useful byproduct. And we can do that with kelp. Some species can grow up to 0.5 meter per day. And if you go into an area where there's a lot of surplus effluent like animal waste and nitrogen coming out to the ocean, then it will grow even faster and you'll get larger strains of it. So, as an exercise, we proposed that there were 9,000 retired oil platforms in the Gulf of Mexico. If you were to take 20 of those platforms and around each platform seed 1 kilometers worth of kelp in each direction and put them at the mouth of the river, it would absorb all that nitrate, all that animal effluent, and you could reel it in, and you can convert 19,000 gallons of ethanol per acre of kelp. The rest would be dry powdered and used as animal feed, and the rest of the chemistry could be processed on board that platform, like some of the salts, some of the magnesiums, some of the other things you would get out of the ocean, like the heavy metals and some of the minerals. All those could be processed on site by the bioethanol that you'd be making from the kelp. So each oil platform would now be a $1 billion factory at sea that would clean the oceans and be self-sustaining within the first 6 to 7 months of operation. I think this is one of our favorite examples of a problem becoming the solution and actually becoming an economically viable program fairly quickly. Now let's look at the next culprit that's fairly well renowned for ocean acidification, and that of course is desalination plants. Now the challenge with this is that we need them. Nobody really wants them because they're not very economically viable and they're very challenging to maintain. So right now there's over 20,000 desalination plants around the world. In the next 4 years, there's expected to be 44,000 of them. And that just makes a larger compounded problem, because if there isn't regulation or policy on how each one of these things should be run for each country, and if everybody's not in agreement, then everybody will be dealing with everybody else's problem. The biggest challenge we have with desalination plants is the byproduct. It's brine. It's very thick, very concentrated salt water that's like molasses. It's essentially battery acid. So like before, we took a really close look at the problem, and we felt there must be something we can do with all this toxic battery acid that's being flooded into the ocean that's creating these dead zones. There must be a product that we can spin out of this that has a good economic gain and will also do something to benefit the environment. So let me be the harbinger of good news here for a moment. Salt is an excellent byproduct, and it's grossly underutilized. Many of these desalination plants have salt ponds, and what they do is they pump the brine into it first, and sometimes they extract the salt off and they sell it, and the rest of the acidic brine is put out to the ocean and sort of dabbled around a large area so it doesn't concentrate too much. But what's not generally known is that 1 acre, 12 meters deep, will produce 800,000 watts of storable solar energy. So that essentially makes it a salt brine battery. Now, if you were to take this idea and concentrate it down into a 40-foot shipping container, as an example, then you might have something that looks like this. So how would something like this work? Well, what you would do is you would take the concentrated brine, which is like molasses, and you would fill 2 40-foot containers. You would paint it black, and the sun would heat that brine up to nearly 100 Celsius. In the bottom of that 40-foot container, you would put a series of coils that are hollow, and you could pump a refrigerant through it, or glycol, which is a very common item used for solar thermal applications. You would take the heat out of that 40-foot container, and you would transfer it to a small box there at the bottom, which has a small closed cycle Freon turbine. So the heat of the box would be used to drive a small closed cycle, zero emission, zero pollution Freon turbine that would be about 125 kilowatts. So if we apply this model to the salt brine pond that's on the side of the desalination plant, that means that every desal plant could potentially have between 50 to 250 megawatts of stored solar thermal energy that it could apply to itself or give to the community. Now, we do have a lot of brine to deal with on a daily basis. In California, they're moving 50 million gallons of water per day in a single plant. So that's going to be a lot of brine. We can't just keep letting it build up and store it. We can utilize it. So what we should probably do is look at a process that can take the brine and separate out the chemicals so it's not toxic before it goes back out into the ocean. There's a process known as plasma water distillation. It's a fairly new technology, but it comes out of frack wastewater remediation, where they would pump all these horrible toxins out of the ground, and the waste remediation groups would be forced to separate the water from all the chemistry, and it turned out there was a lot of brine in a lot of these processes. And through an accidental discovery, when they were running the brine through the plasma water distillation system, it would ignite the salt, and the salt would get up to about 110 to 120 Celsius, which means that you had a thermal reaction by just extracting and pulling the salt out of the water. The energy reaction was so high that it's able to take the heat from it and use it to drive the process. So you get free heat by just trying to pull the salt away from the water. It's a very exotic, very interesting process. Another interesting aspect of this specific application is that it also targets very specific chemicals. You can dial in the frequency to the things you want to remove from the water. When you're running salt water through it, you can ignite the salt. If you're running brine through it, you can reduce the brine down so that it becomes potassium hydroxide and sodium hydroxide. These chemicals are pH balanced and actually safe to put back into the ocean. So unlike the brine, it's completely biocompatible. Knowing now that we can essentially target the type of elements and metals that we want to extract out from the brine, then the next aspect of this would be brine mining. We're not the first to come up with brine mining. This has been around for some time. But we are the first to present a technology that can do it affordably with a very small amount of energy. Usually it's cost prohibitive, which is why it's not a very popular process. Now, when you look at the amount of materials that you get in a single drop of seawater, you can see how this could be a very compelling argument to extract at least a portion of these. Not all of it, but a portion of the brine could be used for metal extraction, and then the rest could be put back into the ocean after it's been reduced down to potassium hydroxide and sodium hydroxide, so it's pH balanced. But I'd like to target two specific items here. I want to talk about salt, and I want to talk about magnesium. So we're very familiar in our company with the power of salt. And here's an example. If you were to take a single teaspoon of salt and heat it up to boiling, which is about 600 Celsius, when you reintroduce the salt back into the water, it explodes in a flash of steam and hydrogen. We were so inspired by this reaction that we started developing a series of motors and turbines to harness this explosion of salt and water. How would you use that to drive an engine? Well, it would work something like this. You would take hot gas or plasma, or an electromagnetic wave like a microwave, and you would heat the salt. You would then combine the salt with the water. It would cause the explosion that you saw, which could be used to drive pistons or run a turbine. What you get as a byproduct is steam and salt water. Now you can use that to condense it and reuse it again, or you can membrane the salt out and get distilled drinking water for an island, or you can exhaust it all out to the sea. It's just salt water. Let's talk about one aspect of salt. Let's talk about the sodium. So salt is sodium and chloride, but let's just take the sodium. By itself, without heating it, it reacts violently with water and it creates a flash of steam and heat. The benefit of sodium is it's used in batteries, and it turns out that sodium batteries could potentially be more powerful than lithium ion, according to recent research. You can also use it for solar energy storage, and it's a chemical fuel. Now let's move on to the 8th most abundant element on the planet, my favorite, magnesium. So magnesium has a very interesting aspect in that it's a metal that burns. So 1 cubic mile of seawater contains about 12 billion pounds of magnesium. There's a lot of it out there. Magnesium is used in batteries, and funny enough, it's an essential food supplement for humans. Let's concentrate for a moment on the aspect that this is a metal that burns, because there's something I'm about to show you that could change the entire future and trajectory of clean energy development. So how can we utilize magnesium as a clean energy fuel that's carbon neutral? You take a laser, you heat the metal up to 473 degrees Celsius. You take this hot magnesium powder and you combine it with water. What you get is a 3100 degrees Celsius flame that is now boiling out the water to hydrogen. You also get steam, and the metal itself turns into oxidized magnesium, which just means it's got a coating of oxygen on it now. The byproduct is you have the world's best water heater. You can have heat cogeneration to generate steam power for power plants or cars or boats or any application you want. And you've got industrial heating for mining applications and for ore refinement. So what we've got here is the transition material that we've wanted to go from a fossil fuel economy to a clean energy economy, and it's one of the most abundant things on the entire planet. It gets better. So what we get is we get heat, we get light, we get steam power, we get hydrogen, we get magnesium oxide. There is no greenhouse gas emissions of any kind when you burn magnesium. It does not have any CO2 in it. But wait, there's more. You can have an infinite regeneration cycle with this metal, because when you're getting an oxygen layer on it, you can remove the oxidized layer with a laser or chemistry, and you can reutilize the metal over and over and over indefinitely. This metal has more energy density per gram than gasoline and can replace fossil fuels, coal, and nuclear energy. This means that every desalination plant could be the fuel provider we need for the clean energy future we deserve. So to summarize, we have a metal that's virtually unlimited, provided by the ocean, that can match the temperature of a nuclear reactor, gives us all the hydrogen we need to transition to a hydrogen economy if we want to, and can effectively replace fossil fuels because it has more energy density, and coal. This is the transition material we needed for a clean energy future. And this concludes our briefing on the blue economy. We hope you enjoyed it. We are Alphacore, and we look forward to working with several of you very soon. Have a good afternoon.